Okay, assalamu alaikum. Good morning, guys. Please just confirm that you guys can hear me and see my screen. Now we can hear you. Okay, perfect. Okay, so good morning, assalamu alaikum, guys. Welcome back to grade 12 physics / chemistry by Inspired Teens. Where in today's lesson, we're going to continue with organic chemistry, right? So I want to get through isomers completely, talk about intermolecular forces and discuss the experiments, and then go ahead and do some practice questions, okay? And then next week we will continue with reactions and then do questions for reactions, right? Okay, sorry, my webcam isn't working because I don't know, something is wrong with it. I think I need to download software or update it or something. I'm going to try and sort it out. So hopefully by next week, it should be fine, but I have actually figured out a way to share the screen without seeing everything else. So it actually should be a lot better for you guys to not see all the other things, the whole interface. So I hope you guys can benefit from that. Okay, let's continue, right? Remember last week we discussed esterification. Okay, we said that esterification is an alcohol plus it's basically the creation of an ester, and an ester is made up of an alcohol plus a carboxylic acid. The catalyst in this reaction is concentrated H2SO4, and it has the following functions. It speeds up the chemical reaction and acts as a dehydrating agent. Okay. Then we gave an example just to show how the reaction works. We gave the structural formula example as well. Okay, so you could be asked to draw this, right? They could say, give the esterification reaction, give the structural formula of esterification between ethanol and propanoic acid, and you'd be required to draw that. Okay, just because you'd have knowledge of drawing structural formulas, right? So in this case, we used ethanol and propanoic acid, and we said that the ethanol actually gives us, for the carboxylic acid, it gives us the suffix YL, and the carboxylic acid for the ester gives us the suffix O8. So it resulted in ethyl propanoate, and we always have water as a byproduct, okay? Then we showed the structural formula. Now, the structural formula, basically, you want to draw ethanol, okay? Whenever you draw any chemical organic compound, okay? Whenever you draw any organic compound, right? What you want to do is you want to start off by drawing the functional group, and that's what we did in each case. So the functional group for an alcohol, we drew OH. The functional group for carboxylic acid, we drew the COOH, okay, which is the COOH. And yes, so when we do it like specifically like this, just to show you that when it forms the ester, what happens is the OH from the alcohol falls and the H from the carboxylic acid falls, and that forms our H2O. Okay, and then whatever's left, basically, so if we ignore this, whatever's left, which is this, okay, that actually forms the ester. And if you look at this, it's the exact same thing as what's on the left. Okay, just obviously a bit neater. And yes, okay, so I hope that makes sense. Whatever's left basically forms together now to form the ester. And we can look at our ester. So our ester, we said that some part of the ester comes from the alcohol, while some part of the ester comes from the carboxylic acid. How do we identify it? There's two ways. You can either note that, okay, the C that's double bonded to the C that's double bonded to the oxygen, whatever C's are attached there comes from the carboxylic acid, and basically the C's that are not attached to the double bonded O, that comes from the alcohol. Alternatively, you could split it by the single bonded oxygen, and then say that everything on the double bonded side, so they both explanations of understanding which comes from alcohol, which comes from carboxylic acid are exact the same. If you understand one, you understand the other. So you can split it by the single bonded O, and whatever's on the double bonded O side comes from the carboxylic acid, whatever's on the other side comes from the alcohol. Please note, you can't generalize and say whatever's on the right and whatever's on the left, because sometimes the double bonded O could be drawn on the left, okay? And then if you're going to assume that the carboxylic acid always comes from the right, it's going to be incorrect in that situation. So don't use left and right. use all oxygens, basically single bonded oxygen, double bonded oxygen. Okay. We said, then we discussed isomers, okay, which are very common. Isomers, compounds that have the same molecular formula, but different structural formula. So we said they have the same amount of carbons and hydrogens and oxygens and whatever else they have, okay, but different structural formula. So the way they are structured is different. Under structural formula, why can't you see me? Yeah, sorry, just my camera this week is not working. For some reason, yeah, yesterday it was causing a bunch of technical issues. I don't know, I think I need to update the firmware or something, but hopefully by next week I will definitely have it sorted out, inshallah. And yeah, the reason the screen is big is I figured out a way to share the screen without you guys seeing everything else, so that it's much better for you guys to see. So it's probably a bit weird this week just seeing big screen and no face. So yeah, from next week we'll get that, so I'll get that sorted out, and yeah, from next week everything should be fine. Okay, so under structural formula we discussed chain isomer, positional isomer, and functional isomer. So let's discuss, okay, whatever. Chain isomer, let's discuss chain isomer, right? Chain isomer, we are staying in the same homologous series, so that the homologous series from one chain isomer to another chain isomer is the same. What is different is the number of branches on the main chain. Okay, so that's what changes. It's the amount that you have in your main chain, okay? The amount of branches you have on your main chain. So that's why we call it the chain isomer, okay? Branches are in different positions. Minimum of 4 carbons. Okay, so what could change is a different number of branches. Keep this in mind, right? What could change is a different number of branches, or the branches are in different positions. So if you move the branches as well, that could be considered a chain isomer to another one. And it requires a minimum of 4 carbons. So we looked at the example of just pentane. Okay, so we have pentane with no branches. Okay, and then what we did was we created a carbon, an alkane, basically, an organic compound with 4 carbons, okay, instead of 5. But that 5th carbon, what we did with it was we made a methyl branch with it. Okay, we created a CH3 branch with it on the 2nd carbon. Okay, in that case, we have pentane and we have 2-methyl-butane. Okay, they sound too different. They have 2 different structures. However, these are actually isomers because they contain the same amount of carbon, same amount of hydrogens, and they have the same molecular formula. If you had to count the amount of carbons and the amount of hydrogens in each of these chemical compounds, organic compounds, you would have the same. Okay, so when we look at pentane and 2-methyl-butane, we say that those are chain isomers. Then we discussed the positional isomer. Now, the positional isomer, again, we are still staying in the same homologous series. We are not changing the homologous series. So, of course, we are expecting the same functional group, right? But what is happening is, yes, of course, we're expecting the same functional group, but actually the main thing of a positional isomer is you are changing the position of the functional group. Okay, so then we split it into 3 different ones where we discussed a functional group, the double or triple bond. So when we change the position of the double or triple bond, so we had the first organic compound was butene. Okay, it's not drawn in with all the hydrogens. Please never do that in your exam. Always you want to draw your hydrogens in. So we discussed butene, where the double bond is on the 1st carbon. Okay, so it's technically like but-1-ene, but we don't have to mention but-1-ene when it's on the 1st position. And then in the 2nd organic compound, we changed the position of that double bond and we moved it to the 2nd carbon. So now we have to label it. We have the IUPAC name is slightly different. It's now but-2-ene. So but-2-ene, we say, is a positional isomer of butene, because it is the same thing, meaning same molecular formula, but its structural formula differs because the position of the functional group is different as well. Okay, so that's an example using, and of course it could work using a triple bond as well. Then we talked about halogens, which creates our haloalkanes or haloalkanes. Okay, and we discussed chlorine, right? So we had 2 chlorines, and then we just moved the position of 1. So the first one is actually 1,1-dichloroethane. Sounds complicated, but it's really not. It just means that on the 1st carbon, we have 2 chloros. That's why we named it dichloro, okay? Dichloro, and then we had 2 carbons, and it's definitely an alkane because it has only single bonds, right? This is a saturated compound, remember? Saturated single, meaning compounds with only single bonds are known as saturated compounds. Okay, so nevertheless, then it's 2, the prefix for that is eth, and then it's an alkane, so it's the suffix is ane, so ethane. So 1,1-dichloroethane. If we move the positions of those chlorines, even just one of them, of course we can only move one in this case, we move it to the second carbon. In that case, it becomes 1,2-dichloroethane. So 1,1-dichloroethane and 1,2-dichloroethane, those are known as positional isomers. Okay. Then we discuss in alcohol, so the same concept, right? Where we're moving the position of the functional group. So what is the functional group of an alcohol? It is what we call a hydroxyl, which is basically OH. This is a hydroxyl. And here again, we have propanol drawn without the H's. Don't ever draw without your extra hydrogens. I'm just doing it because I'm not going to write the final exam for grade 12, I guess. But yes, I'm just doing it because I'm lazy and it's just quickly to understand it. But please don't skip out your H's. You're going to lose marks, okay? And remember, the carbon has 4 bonds, so you need to make sure that you have 4 bonds for each carbon. Anyway, propanol, right? How do we change the position of the functional group? You basically change the position of your hydroxyl functional group, which is hydroxyl, again, is just OH. So instead of being at the first carbon, we moved it to the second carbon. So propanol or propan-1-ol basically became propan-2-ol. Okay, which indicated that the functional group's on the second position. Then we discussed the functional isomer. The functional isomer, this is now when we change homologous series. We move from one homologous series to the next. So when you do that, you actually are changing the functional group. But yes, they still have the same molecular formula, just different structural formulas. And in this case, also different homologous series, different functional groups. Right? Remember, these two work hand in hand. Why? Because each homologous series has its own functional group. Okay, so we then said that our functional isomers, okay, are when we move from carboxylic acid to ester, or vice versa, from ester to carboxylic acid. We move from aldehyde to ketone, ketone to aldehyde. These are functional isomers. So we looked at some examples, right? C4H8O2. I don't know why that's written there. I have no idea why this is open here. Is it supposed to be C5, I think? Let's just change it. Okay, nevertheless, so we first looked at pentanoic acid, okay? And pentanoic acid, we also wrote a chain isomer. The reason we wrote a chain isomer for it, so instead of having pentanoic acid, we basically had what we have at the bottom, 3-methyl-butanoic acid. So we moved one of the carbons, okay, out of the main chain. We created a methyl group with it, and it's basically a chain isomer, right? A different amount of branches in the main chain between pentanoic acid and 3-methyl-butanoic acid. The reason we drew both is because the ester functional isomers, okay, we should actually add one more annotation here to say that. These are what? These are functional isomers. Okay, so between pentanoic acid and what we have on the right, basically, if you're going to go from a carboxylic acid to an ester, you need to draw any ester with 5 carbons because it's pentanoic acid. So any ester, why do I say any ester? Because remember, your ester can be created from an alcohol, is created from an alcohol and a carboxylic acid. So you can have a certain amount of carbons from the alcohol, a certain amount of carbons from the carboxylic acid, and it will be called a different thing, right? You can change the amount you give from alcohol and change the amount you give from carboxylic acid, provided that the total that they add up to is still 5, right? You need to have a total of 5 carbons combined from your alcohol and from your carboxylic acid. So in the first one, what we did was two carbons came from the alcohol, as can be seen here, ethyl, and 3 carbons came from the carboxylic acid. So that was called ethyl propanoate. But then another ester with 5 carbons was when we gave 4 carbons from the alcohol and just 1 from the carboxylic acid, which again is perfectly fine. And that gave us butyl methanoate. Okay, so both ethyl propanoate and butyl methanoate are actually functional isomers of pentanoic acid. Ethyl propanoate and butyl methanoate are functional isomers of pentanoic acid. Okay, and the reason that we added this 3-methyl-butanoic acid is because ethyl propanoate and butyl methanoate are also functional isomers of this guy here. Okay, it's still a carboxylic acid, okay, with 5 carbons, 10 hydrogens, 2 oxygens. It's just that this one has a branch. Instead of having it in the main chain, the fifth carbon, instead of it being in the main chain, the fifth carbon is in a branch. But again, ethyl propanoate, butyl methanoate are both functional isomers of this guy. Okay, just like how they functional isomers of pentanoic acid, they functional isomers of 3-methyl-butanoic acid. And one more thing, if we notice between the two different types of esters that we drew, they are actually positional isomers between each other. They are positional isomers because we have changed the position of the functional group. Okay, the functional group being the COOH, which is in this block. Okay, we can see its position changed. Right here, it's a little bit more central. Here, it's moved completely towards the right because only 1 carbon comes from carboxylic acid, the rest comes from alcohol. Okay, that's all about we discussed. Let's talk about ketone and aldehyde. Notes. Second, alsjeblieft. Okay, let's talk about ketones to aldehyde. So this one is a lot more simpler, a lot more simple. So can someone tell me the IUPAC name of this ketone? What's the IUPAC name of this ketone? What would the IUPAC name of this ketone be? Okay, remember prop is for 3. Here we have 4 carbons. So this is butanol. Okay. Yeah, but correct. Okay, no need to apologize. So but2on, yes, correct. Okay, so you'd actually not but, you'd say butan2on. Okay, so you could also label this as, if you want to specify the position of the functional group, you name this guy butan2on. Why? Because the functional group, which is basically the O double bonded to the C, okay, that is a this is the functional group of a ketone. Okay, now let's convert it to an aldehyde. It's simple because an aldehyde, if you remember, the functional group of an aldehyde is CHO, not CHO, but CHO. Okay, so CHO is at the end always. So we have a C double bonded to an O. We have a C double bonded to an O. Okay, and then bonded to an H. That is the functional group of an aldehyde, and it's always at the end, always at the end. Okay, so we just add 1, 2, 3 more. We fill in our hydrogens. Make sure we only have 4 bonds. Okay, and that is an aldehyde with 4 carbons. Yeah, so basically from ketone to aldehyde. And someone tell me while I explain what's the IUPAC name of this aldehyde. Okay, so what was I saying? Yeah, so basically an aldehyde is a ketone with the double bonded O to the C, which is at the end of the organic compound. And then a ketone is an aldehyde, but the double bonded C to the O is in the middle of the compound. Okay, so basically when you take the middle double bonded O to C to the end, it becomes a ketone. It is butanol, that is correct. Butanol. Okay, an aldehyde with 4 carbons. Cool. So that's isomers, guys. That's all the isomers you need to know: chain, positional, and functional. Okay. And then within functional, we have within positional, we have double or triple, or we just have the different examples. Okay, and then functional isomer. Yeah, between carboxylic acid, ester, aldehyde, ketone. All right. Isomers. So let's move on to intermolecular forces. Won't we lose marks for not specifying the functional group? So you see, with something like butane 2 on, okay, depends on your marker, because you see butane 2 on is actually the second position of the carbon is the closest you can go to the edge of this compound, because as soon as if you're going to put the double bonded over here, it's going to become an aldehyde. So in this case, right, this is butanol. If you have to ask what is butanol, then okay, if you have butane 2 on and you have butanon, okay, so if you have butane 2 on being this, what would be butanon? Okay, you cannot have the O double bonded to the C at the first carbon, and therefore this is what we would regard to what we would call butanon. So similarly, as to how you don't have to call this butane 1L, okay, this one it might be a bit more lenient where you can call this butanon. Okay, just because it's the basically equivalent of like when the functional group is on the first carbon. Okay, in this case, it has to be its first carbon. It has to be on the second carbon, because if you're going to move it to the first carbon, it's going to become an aldehyde. Okay, so yes, always specify though. Always specify. So if you have the option between writing butanon and butane 2 on, I would definitely write butane 2 on. Okay. However, like I said, for this one, they might be a bit more lenient if you say butanon because of its position. It's like this. Instead of calling this butane 1L, you just call it butanol. Okay. I hope that clarifies. Sorry, someone had a question. Okay, let's talk about carbon, not carbon. Let's talk about the intermolecular forces, okay, found within organic chemistry and how we have to utilize it. Don't worry, you don't have to know much. Intermolecular forces is not coming back to haunt you from grade 10. Okay, so when we talk about the intermolecular forces, firstly, we state that the carbon chain that's part of any homologous series contains London forces or London dispersion forces, which are also known as induced dipole forces. Okay, so yeah, you don't need to know what induced dipole forces are. You don't need to go into the details of intermolecular forces. That was we left that behind in grade 10. Here we are interested in the intermolecular forces, right? How do they relate to our organic compounds, and how do we compare different organic compounds based on their intermolecular forces? That's what we are interested in for this section. So yes, you need to note that the carbon chain that any homologous series has London forces between carbon and carbon. Then we talk about the strength of intermolecular force. It is directly proportional to molecular size. Okay. So the more carbons you have, the stronger your intermolecular forces are. Okay. Then we look at the different homologous series to discuss their respective intermolecular forces. So the single bonded alkanes, not the single bonded alkanes, the hydrocarbons, okay, which are your alkane, alkene, and alkyne, they all have London dispersion. Okay, then we talk about the haloalkanes, okay, which is our alkanes, but with halogens. These have dipole forces. Okay, then when we talk about hydrogen bonding and carboxylic acid, when we talk about alcohol and carboxylic acid, these are the two that actually have hydrogen bonding. Okay, then when we go to esters, aldehydes, ketones, all of these have dipole forces. Okay, so hydrocarbons, London dispersion or London forces. Haloalkanes, esters, aldehydes, and ketones, they contain dipole-dipole forces. Okay. Alcohols and carboxylic acid, hydrogen bonding. So remember from grade 10, what creates a hydrogen bond? When you basically bond H with F, or H with O, or H with N. Okay. H with any of these, this would create hydrogen bonding, which is very strong, right? So when we have an alcohol, right? Remember the alcohol bonds with O bonds with H. Okay, so that creates the OH bond, which is hydrogen bonding. In the carboxylic acid, the O bonds with H as well. Somewhere along the line, the O bonds with the H, and it creates hydrogen bonding. Then we can talk about the order, the strength. Okay, so this here, what's represented here is the strength. The strength of intermolecular forces. So hydrogen bonds are stronger than dipole-dipole bonds, which are stronger than London forces. Okay, so the strongest are your hydrogen bonds, then it's your dipole-dipole, then it's your London forces. Okay, now in hydrogen bonds, we have two different examples of hydrogen bonds. The one is a carboxylic acid, the other one is an alcohol. Okay, now carboxylic acids actually have stronger hydrogen bonds than alcohol. And the reason for that is, because you could be asked the reason, you need to know, is that carboxylic acids can form two hydrogen bonds per site. Okay, so that's the main thing. So if you had to ever compare carboxylic acids and alcohols, that's what you would say. Okay, let's talk about the experiments. Okay, so we're going to go through the three different types of experiments that you could deal with. Okay, maybe what I'll do is I'll try and make these notes a bit more clear, but nevertheless, we have experiment 1. Now on the leftmost column, you can see the headings: dependent variable, independent variable, control variable. That's it. Okay. So in experiment 1, the dependent variable is boiling point. So remember in experiments, right? Your dependent variable, right, is what changes or what you change. Okay. So in this case, the dependent variable is boiling point, which means that the boiling point is being changed. Your independent variable is what's being affected by the dependent variable. Sorry, I mixed the two up. Let's start again fresh. Okay. So we say that your independent variable, this guy here, this is the one that you change. Okay. Or this is the one that changes in the experiment. Okay. And it is independent, right? It's the one that's changing first. Now the dependent, which comes from the name, it is dependent on something. What is it dependent on? It is actually dependent on the independent, meaning it is dependent on what is changing. So as the independent changes, the dependent changes as well. So in this case, the dependent is boiling point. So basically we're saying as the molecular size is changing, that's affecting the boiling point. The boiling point is changing. Boiling point, or MP, meaning melting point. Boiling point or melting point, they're very similar and they would both be affected in the same way. So whether the experiment includes boiling point or melting point, it doesn't matter. Now, the control variable is the homologous series or the structure, position on the functional group. Okay, so that's all theoretical. Let us, it's more like summarize, so that when you understand it, it's easier to come back to that, right? So let's talk about what are we exactly talking about. So basically, we're dealing with this example. So just look at the example here. Okay, we're just looking at this. Okay. Methane to octane. Okay. So we are dealing with alkanes only, because methane to octane. We are starting off with one carbon in an alkane. We are moving on to 8, all the way to 8 carbons, which is octane, all the way to 8 carbons. Okay. Now, okay, so let's read it. It says, as more carbon atoms are added to alkanes, the molecular size increases. Naturally, that makes sense. As we add more carbons to alkanes, so we go from methane, ethane, propane, butane, pentane, hexane, heptane, and octane, I think, right? So as more carbons are added, the molecular size increases. The London forces between the molecules of alkanes become stronger. So you see, the key thing is the forces become stronger because of increase in molecular size. Forces become stronger because of increase in molecular size. Maybe we can add that. So the forces, regardless, irrespective of what they are, okay, they could be your London dispersion forces, they could be your hydrogen, they could be your dipole forces, okay, irrespective of what they are, because we are increasing the molecular size, the forces are going to increase in magnitude as well. The forces are going to become stronger. In this case, we specifically mention London forces because we are dealing with alkanes, and we know that alkanes have London dispersion forces only. So that's why we say as more carbon atoms are added to alkanes, molecular size increases, the London forces between the molecules of alkanes become stronger. If we were comparing two compounds that have dipole forces, okay, as the molecular size increase, the dipole forces between the molecules would become stronger. Okay, let's go again. As more carbon atoms are added to alkanes, molecular size increases. London forces between the molecules of alkanes become stronger. More energy is required to overcome the attraction forces between the compound, resulting in a higher melting point or boiling point. So that's experiment 1. Let's have a look at experiment 2. Okay, so yeah, just to reiterate, experiment 1, our independent variable is molecular size. Our dependent variable is boiling point. I think maybe what I'm going to try and do is to redo these notes in a bit of a better structure. Redo these notes as well as, yeah, okay. Just I think I'd like to put the independent variable first now. So it makes more sense and it distinguishes experiment 1, experiment 2, and experiment 3. So the independent is molecular size. So that's the one that's changing. The dependent is boiling point. So the boiling point and melting point is being affected by the change in molecular size. The control variable is homologous series. Remember, the control variable is what you need to keep the same in order to keep a fair experiment. Okay, you can't change more than 2 things and then make a decision. Okay, just say you are trying to figure out what's a very simple example? Okay, let's just say you're growing a plant, okay, and you're trying to figure out why your plant is growing so slowly. So currently you have it indoors and you don't water it, okay? Now you take your plant and you put it outside in the sun and you water it, okay? In that case, okay, and then just say you put it outside and you water it and now it grows. You wouldn't really be able to tell what made a difference, okay? Okay, obviously in this example, we know it's both because plants need sunlight and water, but I think you get my point, right? Where if you're going to change 2 things, then you can't conclude anything. So in this case, we're only changing molecular size, because if we're going to change molecular size, homologous series, structure, we're not going to be able to identify a relationship here, right? So the control variable here is the homologous series. You are keeping the same homologous series and the same functional group basically, and structure, including position of the functional group. You are keeping the position of the functional group the same and the structure the same. So in this case, they say mention about London forces only. Okay. So methane to octane, methanol to octanol, that would be for alcohols. Okay. So what do they say? Mention about London forces only. So yes, sorry. Earlier I said that you can mention the, what you call them, the other forces, dipole. No, because remember, let me just clarify this. Because when we move from methane to octane, what is changing is the amount of carbons in the main branch. So what's the carbon main branch? Remember, we said that the carbon main branch has London forces only. The carbon main branch has London forces only. So if you are going to take the carbon main branch and increase it, you are only affecting the London forces. So irrespective of which compound you're comparing, methane octane, methanol octanol, whichever you are comparing, you will only mention London forces. We mention about London forces only. As more carbon atoms are added to alkanes, molecular size increases. London forces between the molecules of alkanes become stronger, more energy required to overcome the attraction forces between compounds, resulting in a higher melting point or boiling point. Remember, this could also be lower. Okay, depending on what? Depending on if you're decreasing in molecular size. If you're decreasing in molecular size, then everything here would be opposite. Okay, let's look at the next experiment 2. So in experiment 2, the independent variable is the homologous series. So now we are changing the homologous series. Okay, so we're changing the functional group. The control variable is molecular size. So we're keeping the molecular size the same in this case. And the dependent, okay, is boiling point. All right, so again, boiling point is being affected. So let's read the thing first and we can go back to the notes. We're reading the middle column, okay, right here. Compound C, okay, let's look at the example actually, sorry. What are we comparing, okay? We say intermolecular forces between molecules, we are comparing the strength of intermolecular forces. So we deal with propanoic acid, butanol, and pentane, okay? So oftentimes, I know here it might look like, what are we changing? We are changing functional group, and we are changing amount of carbons. We are changing functional group, and we are changing amount of carbons. In this particular case, okay, the only one we look at is change of functional group. The reason as to why the amount of carbon, carbons are changing are because they are similar molecular size. So we actually trying to keep it fair by keeping them similar in molecular size. We're keeping it more fair. So that's why we're comparing propanoic acid to butanol to pentane, because these three of different functional groups are similar molecular size. So that's the reason why we're not comparing propanoic acid and propanol and propane in this specific case. So in those cases where you're changing functional group and you're changing, amount of carbons, we would go for the changing functional group. Okay, so compound C has London forces between molecules. So compound C is pentane. There's London forces, that's true. Compound A and B have hydrogen bonds as well as London forces. So A and B, which is a carboxylic acid and an alcohol respectively, they have hydrogen bonds as well as London forces. Hydrogen bonds is stronger than London forces. So basically, we are saying the hydrogen bonds of A and B are stronger than the London dispersion forces of C, which is pentane. That's what we're saying, okay? However, but the hydrogen bonds between molecules of compound A is stronger than compound B. So we've already established that compound C is last because it has London dispersion forces only. Okay? It has only London dispersion forces. And then we say that compound A and B have hydrogen bonds, so it's definitely stronger than compound C. Okay, and then we compare between compound A and B. So we say that between compound A and B, okay, the molecules of compound A are stronger than compound B. This is because so basically you're saying the hydrogen bonding of compound A is stronger than the hydrogen bonds of compound B. Why are you saying this? It's because compound A can form 2 hydrogen bonds per molecule. Okay, then we have, it says most energy required by A and the least by C. So A, the strength in the molecular strength of A is greater than that of B, which is greater than that of C. Let's look at the notes. It says mention about the different types of intermolecular forces between molecules and then compare the strength of intermolecular forces. Makes sense. Let's look at experiment 3. Again, dependent is boiling point and melting point. Independent is the number of branches. So now we're changing number of branches. So we're basically working between chain isomers. Okay. The constant or the controlled variable is the homologous series. So we're keeping the homologous series the same, and molecular size. So in this case, we're not changing molecular size. Okay, again, we change molecular size there because these were actually physically similar. So let's look at what we're comparing. We are comparing, if we look at this, we are comparing all of these compounds, A, B, and C, have 5 carbons. So the first one, let's see, you guys give me the name. What's the name of the first compound? Quickly, let's see if you guys are awake. Pentane, very good. What's the name of the second compound? What is the name of the second compound? 2-methylbutane, very, very good. What's the name of the third compound? Correct. Second one, 2-methylbutane, very good. And finally, yes, the third. 2,2 propane, no. 2,2 dimethylpropane, no. 2,2 dimethylpropane. 2,2 dash dimethylpropane. Okay, don't forget the 2,2. You have to mention both numbers and the di. Okay, so what happens essentially, okay, so here they tell us also, mention about London forces only, and we say that as the number of branches increases, the surface area decreases. So as you can see, if we have to compare A, B, and C, the surface area of A is actually the largest, and the surface area of C is the smallest. So London forces become weaker. We say here, compound A has the least amount of branches and therefore has the largest surface area. Compound C has the most branches and has the smallest surface area. The London forces between C is the weakest and the London forces between A is the strongest. Okay, that's due to the surface area. More energy is required to overcome the attraction forces between compound A. So the higher the higher the surface area, the stronger the intermolecular forces, more energy required to overcome attraction forces between compound. Therefore, A has the highest boiling point, then it's B, then it's C. So it's a quick note here that says less branches, higher surface area, stronger intermolecular force, higher melting point, boiling point, straightforward. The bottom one, more branches, has a lower surface area, which results in a weaker intermolecular force and a higher melting. No, that's wrong. It's supposed to be lower. Lower melting point or boiling point, because if the intermolecular forces are weak, it doesn't take much heat to melt them or to boil them. Okay, so that's the 3 different experiments. Let's have a look at a question. We'll start off with the November 2021 paper. And we're just going to answer it and just rapid fire it, right? So the letters A to H in the table below represent 8 organic compounds. Okay. 2.1. Define the term unsaturated compound. Someone tell me quickly. I think the Zoom is a bit delayed, but it's fine. Unsaturated compound. How would we define such a thing? Anybody? Nobody? Okay, let me define it quickly. An unsaturated compound. New. Not only single. Saturated is what's single. Here's the memo definition. A compound that contains a double bond or multiple bonds or does not contain only single bonds between carbon atoms. So a compound, I would say a compound that contains two or more bonds, not only a single bond between carbon atoms. Correct. I think most of you have it, right? The memos I have attached here, so you can go through them to look for memo answers. Also, if I'm not mistaken, I uploaded, I don't think I told you guys, I uploaded two things. I uploaded the memorandum guidelines or the marking guidelines or whatever it's called. I think it's the memorandum guidelines onto the Google Drive where you can find all the definitions. Secondly, in the group description, there is a link to past papers. Okay, an excellent website which you need to use. It contains past papers and memos for past papers. So please make sure you use it. Okay, write down the letter that represents an unsaturated compound. Okay, give me. Letter that represents unsaturated compound. Basically, we're looking for a double or a triple bond. That's it. Someone says B, and indeed B would be correct. Okay, correct. Well done. Compound. Very good. B would be correct because we can clearly see the double bond. Okay. Okay. Let's talk about, okay, another example could be this, by the way, because this is C2H4. It is basically CnH2n, which is the molecular formula for an alkene. By the way. So yes, B or E. Right, let's see what's next. Name the functional group of compound C. Okay, so the best thing is, I'll do this one with you guys. The best thing is to always draw it out. Not A. Okay, so someone said A. That's interesting because we can see a double bond between oxygen. So you wouldn't pick A because when we talk about saturated or unsaturated, we talk about double bonds between the carbon atoms. Okay, so in that case, that is a carboxylic acid. I hope I didn't give an answer away already. That is a carboxylic acid, and it has a double bond between the carbon and the oxygen. So that's not between carbon and carbon. When we talk about saturated and unsaturated, we're looking between the carbons. Okay, so we talk about B or E. Name of functional group of compound C. Okay, so yeah, I said I'll do this with you guys because we draw it out. Okay, so we talk about the semi-condensed structural formula, which we need to convert into a structural formula. So that's pretty simple because you follow order. So let's start off with our first carbon. I can see that this first carbon has 3 hydrogens attached to it. Then I can attach it to the next carbon, okay, which is this guy. And this carbon has 2 hydrogens attached to it. Then I attach it to this carbon, which again has 2 hydrogens. Then we attach it to this guy. Okay, then it has a bond to an O and then a bond to a CH3. It has a bond to an O and it has a bond to a CH3. So how would we draw this? Okay, the way we draw this is, firstly, number 1, you need to be able to tell that this oxygen here is attached to this carbon before it, and then this carbon is attached to another carbon. So I can draw the next carbon, okay, and this carbon has CH3. Okay, then we have this oxygen left to draw. So this oxygen has to be here. Okay, but now if you look at it, so I've drawn it in. Okay, I hope this makes sense. Up until this point, it makes sense of how I've drawn it from the semi-condensed. Because CH3, check, CH2, check, CH2, check, CO, check, CH3, check. I have everything that's in the semi-condensed. I'm not missing anything. I have everything that's in the semi-condensed. I have it in my structural formula. There's one thing that's missing though. Every single carbon has to have 4 bonds. If I check him, 4 bonds, 4 bonds, 4 bonds, 4 bonds. This does not have 4 bonds. Okay, so that does not mean we add another H. That no, we don't add another H because it's not in the semi-condensed. That means that it is double bonded to this oxygen. That means that it's double bonded to this oxygen because that's all the chemical compounds that we have in our semi-condensed. Okay, so we can't put anything else. Okay, and if we have an H, like in that case, that would have to mean that it's double bonded to the oxygen. So that's how you'd be able to tell whether something has a double bond or even a triple bond. Okay, by looking at the semi-condensed, this is definitely bonded to that, and analyzing that, okay, this carbon needs to have 4 bonds, and it's not bonded to anything else because I can see in the semi-condensed it's just bonded to this one oxygen and then the next carbon. So it uses up 2, so that would mean it's double bonded to that oxygen. So this actually is a okay, tell me at least what functional group. I don't want the name of the functional group, sorry. What homologous series does this compound belong to? What or which homologous series does this compound belong to? Ketones, right? Very good. This is a ketone, right? It's a ketone. And if we recall, let's go back to our notes. The name of the functional group of a ketone is a carbonyl. So in that case, this guy, the name of the functional group is carbonyl. Okay. Cool, man. Cool. Okay, perfect. So let us end it there, right? Where next week I would have loved to finish an entire question today, but that's just how it goes. It's a massive section. So yeah, it can take some time. Perfect. So, okay, cool. I hope you guys are enjoying the lessons just as much as I am. If you guys are benefiting and you guys are enjoying it, you guys are learning, please, again, if you guys have any queries or anything, feel free to message on WhatsApp or whatever it is of your concerns. I know that some of you might have asked some questions in this week. I just haven't had time to respond. And probably next week also. It's just that in the week I'm a bit crazy. I'm busy with exams currently. So I don't have time to respond, and I'll try my best to respond thereafter. But yeah, and otherwise, if you guys are on holiday, enjoy your holiday. If you're still writing, all the best. I will see you guys next week, same time. Thank you guys so much for joining. Jazakallah khair. No problem, no problem. But yeah, what do you guys think of the screen sharing also? It's much better, right? It's much bigger. You guys can only see the content. Yeah, from next week, hopefully, when I get this camera set out, then my face will be on the top left, so you can see me screaming at you guys. But yeah, I think this layout is much better. It's neater. You don't see everything else. So from now onwards, it will look like this. Problemo. Okay, but yeah, thank you guys so much. All the best. Okay, Assalamu alaikum.